I will introduce Gregory Sulley from Oxford, who's looking at switchable catalysts for the preparation of CO2-derived polymers, and the case of heterodinuclear Zn and Mg organometallic catalysts. So.
Okay, yeah, thanks, Josie. Yeah, so I'm Greg. I'm from the Williams Group at Oxford, and yeah, so this is sort of a presentation of some work that I did earlier on during my PhD, and it's looking at essentially the preparation of CO2-derived polymers using these like a developed heterodinuclear catalyst and employing it in switchable catalysis. So just an outline of sort of the research focus of the Williams Group, also particularly one area that we're interested in is the metal catalyzed polymerizations to prepare these oxygenated polymers. And these could be both homopolymers and block copolymers. And in order to do this, we sort of exploit multiple polymerization mechanisms that can be categorized into two main areas, and that's the ring opening copolymerization and the ring opening polymerization of various monomers. In the ring opening copolymerization, what we're looking at is making sort of alternating backbone structures of either epoxide and CO2 to prepare a polycarbonate, or epoxide and hydride to prepare a polyester. In the case of the ring opening polymerization, what we're looking to do is use metal complexes to control the ring opening of either a lactone or a cyclic carbonate to prepare either a polyester or a polycarbonate that way. And ideally what we want these catalysts to be able to do also is to link these different polymerization cycles, as in that way we can exploit quite a large monomer pool to be able to sort of couple these together to prepare various block architectures. So the catalysts that we look at in the group, there's quite a wide variety that we're investigating and interested in, but one of the most widely studied in our group is these dinuclear metal complexes, which are based on this macrocyclic ancillary ligand. And the way to get between one and the other is sort of just a metallation reaction to form the dinuclear metal complex. And we've sort of investigated various combinations of metals in the pockets there with various co-ligands in the R group position. In sort of more specific to my work, I wanted to highlight two key advances with this class of catalyst. And those are in the case of sort of where you have both metals are zinc and they both bear these aryl co-ligands. They found that they could control the co-ligand species by either insertion of a CO2 into the metal aryl bond or protonolysis with an alcohol or similar species. And in this way, they can control the initiating species and control the metal polymer chain end. So this is sort of one aspect to bear in mind in terms of the polymerization mechanisms that I'm targeting and the polymers that I'm trying to prepare. The other one is in the case of where there's a heterodinuclear complex this time, and specifically metal 1 is zinc and metal 2 is magnesium. And in this report of one of the first reports of the heterodinuclear complex, they bear bromide co-ligands. And what they found here was enhanced activity for the heterodinuclear over the homodinuclear analogues, that being either magnesium-magnesium or zinc-zinc, and indeed a 1-to-1 ratio of the two. So from this, they inferred that there was some sort of metal cooperativity between the two sites in the catalysis. And this is facilitated by them being held in a close proximity. And this has since been probed in subsequent studies on this complex and various other metal combinations, both theoretical and experimental observations to sort of probe this synergic effect between the metals. So just going back to the di-zinc complex, this has been utilized further in the preparation of block copolymers. So in this example here, they've used it to prepare these multi-block polyesters, and these function with quite promising elastomeric properties. So these are sort of the end goals of using this catalysis to prepare these materials. And it's been used to elicit block sequence control to prepare well-defined pentablock copolymers from sort of a mixture of monomers in the starting feedstock. But there's no sort of, before I started my PhD, the work on using the heterodinuclears hadn't really been employed in the same way in these switchable polymerizations. So this is something I started initially to work on, and it was specifically targeting the linking of these two particular cycles, that being the ROP of a lactone, specifically decalactone. So the R group is an N-butyl chain, and the ROCOP of CO2 and epoxide, and the epoxide chosen was cyclohexene oxide. And I wanted initially to use a heterodinuclear zinc magnesium catalyst with benzoate coligand. So it was a later derivative of the bromide that showed enhanced activity for the ROCOP. And in linking these cycles, the aim was to generate these ABA triblock copolymers, with a central block being a soft block in the decalactone and the polyester with a low TG, and the two outer blocks in the polycarbonate possessing a high TG, and that's the block that incorporates the CO2 as well. So starting out, you can see here when we use the benzoate coligand. So when we use the benzoate coligand here, we actually see in the GPC, sorry, I should just say this is the polymerization of just the decalactone at this point. So the first stage of the polymerization. And from this, what we need to achieve is a telechelic mid-block to be able to grow the blocks from either end to make that triblock structure. So in this case, when we have the benzoate coligand and 8 equivalents of our bifunctional chain transfer agent, you can see in the GPC analysis, we have this little bump or shoulder at lower molar mass. And when we probe this via MALDI-TOF mass spectrometry, you can see that there's 2 distributions of polymer chains, and one is attributed to the initiation from a coligand, and one is attributed to sort of the telechelic distribution that we're after. And so they correspond to these initiation pathways. The first one being the cleavage of the coligand by the sort of alcohol species in the CTA to generate the metal alkoxide, and then that proceeds to ring open the decalactone. In the other case, the coligand itself can ring open species present in there to form the metal alkoxide, which can then go on to ring open the lactone. So that's how the 2 distributions are generated. So an initial strategy to try and combat this was to basically just increase the equivalence of chain transfer. And if you can see, if we increase it significantly to 20 equivalents, the distribution corresponding to the coligand initiated chains is suppressed, and we have a monomodal GPC trace. But this comes at a cost of significantly reducing the molar mass of the polymer chains, and this is sort of detrimental to the effort of forming these triblocks at high molar mass to try and access sort of mechanically robust materials. So this is not ideal. So then taking inspiration from the di-zinc catalyst with the aryl co-ligands and the control it offers over chain end, I then synthesized the zinc magnesium heterodinuclear catalyst with aryl co-ligands, in this case C6F5. And you can see in this case, when we here we can employ far fewer equivalents of chain transfer, and this benefits us in being able to achieve higher molar mass materials, and more importantly, the distribution arising from co-ligand initiation is completely suppressed. So we only initiate from the pathway of the CTA displacing the co-ligand to form these hydroxyl telochelic chains. So then if we look at the two constituent reactions, the polymerization mechanisms in the rho-cop and ROP of our respective monomers, and we compare the catalyst that we have here, you can see that in the case of the zinc magnesium aryl catalyst, we see in the case of rho-cop pretty comparable activity to the zinc magnesium benzoate, and quite enhanced activity for the ROP. But importantly, comparing it to the di-zinc phenyl, as the obvious question is, if you want control over the chain end, just use the aryl co-ligand catalyst that we already have, or we can see a huge enhancement to the rate there. So we can benefit from that in being able to prepare these materials on a much more reasonable time frame. So then actually preparing the triblock, we utilize the switch catalysis and the switchable nature of this catalyst. And this is dictated, or the ability for it to have control over block selectivity is dictated by the relative rates of insertion and ring opening of the monomers and the stability of the intermediate. So if we look at the cycles over here and the relative rates of each step, you can see that CO2 insertion is the fastest by far, and the ring opening of the epoxide is the slowest, and the ring opening, the insertion and ring opening of the decalactone is somewhere in the middle. So if we start under an atmosphere of nitrogen, we can form this PDL mid block and then insert the CO2, which or pressurize with CO2, which then preferentially inserts, and then we build up the triblock that way. And we can monitor this reaction in a variety of ways. So as the reaction is proceeding, we can follow it by in situ IR, and we can monitor bands for both the formation of the polyester block and the polycarbonate block, and we can see monomer selectivity at the point sort of where we pressurize with CO2. We inhibit the further polymerization of polydecalactone, and we start to see introduction of the PCHC end blocks. And then in order to prove that we have connectivity of the blocks and not just the formation of two homopolymers, and that the cycle is linking, the catalyst is linking those two cycles, if we look at the sort of aliquots of the reaction by GPC, we can monitor the progression of molar mass before and after we introduce the CO2. And the fact that we retain a monomodal distribution with a narrow dispersity is quite indicative that we're forming the block in that sense. We can double check this on materials at the end by using an N group titration using phosphorus NMR. And we can see that when we do a control with just a mixture of the two homopolymers, this is where the N groups appear. And then in our triblock material, we only see the PCHC N group. So that decalactone or polydecalactone mid block is capped. So then moving on from this, with the success in switch catalysis of the heterodinuclear zinc magnesium catalyst, what I did was then built up this sort of library of materials, changing the weight percent of the hard block in it, and in by extension the weight percent of CO2 incorporation into the polymer. And they can be characterized with thermal analysis. And you can see that we have quite a range of material properties. So the green ones here, highlighted in green, form quite stable, flexible films. The one highlighted in yellow is is more viscous, and the one in red is very high weight percent of hard block and is still relatively brittle. But if we take sort of the leading examples of each, so in the case of high CO2 incorporation at 16 weight percent and 50 weight percent of the polycarbonate, what we have is quite a toughened thermoplastic, and this is due to it having an increased extensibility versus the like PCHC or the polycarbonate on its own, and that's due to the incorporation in this block structure, and the decalactone tempers that, or the brittleness of the polycarbonate. Conversely, if we look at something with a very low weight percent of PCHC, so most of this is the polydecalactone polyester, this functions as quite high performance, high shear, permanent pressure sensitive adhesive, with competitive properties to a number of literature examples of pressure sensitive adhesives, and outperforms sort of commercial examples. So in conclusion, we looked at sort of the catalyst optimization and the formation of this heterodinuclear zinc magnesium catalyst with these aryl coligands, which enabled us to inhibit the initiation from the coligands. And in doing so, we were able to prepare a variety of materials, these triblock materials, with varied CO2 utilization, and the weight percent of that could be controlled quite well in the backbone of the polymer by virtue of the selectivity of the catalysis. And these materials displayed relatively high performances with and their mechanical properties were tunable in varying the block ratios. So with that, I've no idea if I've stuck to time or not, but I'd like to thank a few people who were involved in this project. Professor Charlotte Williams, obviously, Doctors Georgina Gregory, Leticia Penecaradeguas, and Thomas Chen, who formed sort of a polymer materials sub-team, and Dr. Kinyanyili, Professor Clive Cillier, and Dr. Nick Terrell for assistance and expertise with various analysis and analytical techniques. I'd like to thank you all for your attention, and I'll take any questions.
Thank you very much, Gregory. Thank you very much for a great talk. If anyone has any questions, please type them in the Q&A. Again, you'll have to forgive me. It's probably been, I don't want to admit how long since I did my degree and did polymers, and I've not done polymers since then. But how modifiable is this to take different monomers to create sort of different types of polymer or different properties?
Yeah, I mean, that's a great question. So the catalyst itself, the one I've developed and have been using here, it's pretty robust to a variety of alicyclic epoxides, and also a variety of lactones that are generally easily polymerizable. And this one, in my work, I haven't tested it too much with anhydrides, but it's been tested elsewhere with looking at using various tricyclic anhydrides, for example, derived from terpenes or other renewable sources. So it's quite applicable to a variety of monomers. Derivations of this catalyst, changing sort of, rather than just the metals, the backbone structure, can help with polymerizing more epoxides derived from propylene oxide that don't have the rigidity of a cyclohexyl ring. That is where this one in particular falls short. It struggles to polymerize those kinds of epoxides. But yeah, you can form a variety of soft and hard blocks using this one.
Oh, fascinating. Does anyone have any other questions for Gregory? I don't see any hands up or any questions being typed, but maybe I'm just going too fast for people's typing skills. Oh, we have got, Andreas has asked, have you looked at what pressure CO2 insertion becomes competitive with ROP to make randomly distributed copolymers?
So this catalyst performs at 1 bar pressure of CO2. So it's generally, it will outcompete the ring opening polymerization at pressures as low as 1 bar. Others require higher pressure. So different metal combinations or ligand structures require higher pressure, and it tends to be, so I should say that with the material preparation in this work, even though the catalyst works at 1 bar, I have prepared them all using 20 bar pressure of CO2, as it just enables sort of better CO2 saturation and limits the side reactions that come from the CO2 insertion and backbiting at higher pressures in that sense. But yeah, I hope I've answered your question, Andy. It generally outcompetes at 1 bar with this one. So I think we haven't seen any evidence for in my work that it forms a randomly distributed copolymer. Okay,
thank you very much. Last seconds to ask any questions. I'm conscious that we've gone slightly over the hour allotted and people may need to leave for other meetings. Well, I'd just like to thank all our speakers again, 3 excellent talks, and good luck with the rest of your PhD, final year and write-up. I look forward to hear of your success at your Viva, and best of luck for the future. Many thanks, everyone, and I hope to see you. Corinne just has an advertisement for the RSC Early Careers event, which is on the 30th of April at 2 p.m. You can go via the RSC Applied Catalysis group, and the link is in the chat if you would like it. And we have a dynamic webinar program with further webinars in May and June, July, August, and going on from there. Our next speaker is Elena O'Reilly, which will be a really interesting webinar on biocatalysis. We look forward to that very much. Stay safe, stay well, and I hope to see you soon. Thanks again to all our speakers. We'll end the webinar now.